All right, good afternoon, everybody. So the plan for today is to finish off the dynamic memory allocation notebook, and then we're going to put dynamic memory, what we've learned about dynamic memory allocation into use to make our own data type. So we're going to implement a string class. Well, not a string class in C. So in C doesn't have classes. We're going to implement a structure in C that looks or resembles a Python or Java style string. All right, so to finish off the memory allocation notebook, we need to talk about two more functions. The first function is realloc. So realloc is the function that you use if you have an existing block of memory that has already been dynamically allocated, and you would like to change the size of that memory block. So for example, you'd like to increase the size of memory that you have, or you'd like to decrease the size of the block that you have. The way you use realloc is you call the function passing in a pointer to the start of the memory block that you want, whose size you want to change. And then you say, how big should that new block of memory, how big do you want the block of memory's new size to be? It can be greater than or less than the existing size. Realloc returns a pointer to the new block of, so the possibly new block of memory that will be reallocated by the function. When you call realloc, the pointer that you pass in here, that has to be a pointer to a block of memory that was previously allocated using either malloc or calloc, or possibly realloc. Right, so you can only reallocate an existing block of dynamically allocated memory. If you just have some regular old pointer, you can't just call realloc on that. It's not going to work properly. As with all of the memory allocation functions in C, you should avoid passing in 0 for new size. Right? You remember the smallest block of memory that you can, the smallest block of memory that you're supposed to allocate is at least 1 unit big. The function will return null if it can't reallocate the block of memory. So if it can't change the size of the block of memory for some reason. Conceptually, what realloc does is the following. So conceptually, it allocates a new block of memory of size, new size. It then copies that many bytes from your original chunk of memory into the new block of memory, right? So if it's smaller, it only copies in the smaller size, the smaller amount of memory, right? If it's larger, it copies in all of the previous memory plus some extra into the new block. Sorry, if it's large, if the new size is larger, it copies the existing chunk of memory into the new chunk of memory. It then frees the previously allocated block of memory, and then it returns a pointer to the newly allocated block of memory. Now that's conceptually what it does. In reality, what might happen is that realloc might be able to change the size of the existing block of memory in place. So in other words, it might be able to expand or decrease its size in place, depending on what the operating system memory manager allows it to do. If that's the case, regardless of what actually happens, anything that was in the old block of memory is now in your new block of memory, right? So it's like changing the size and then copying the stuff from the old block into the new block. So here's an example where we're going to use realloc to reallocate a string. We're going to start by allocating 5 units of memory using malloc, and we're going to write a string into that memory. So we use string copy to copy the string CISC into our chunk of memory. This is safe because CISC has 4 letters in it. It's a string, so there's a null terminator. Right? We need 5 characters, and we have 5 units of memory in str. So if we print str, we should get CISC. We then like to expand the size of str. And so what you do is the following. You call realloc. You pass in a pointer to the chunk of memory that you would like to reallocate. So I'd like to reallocate str. You tell it how big do you want your new chunk of memory to be. So I'd like it to be 8 units large. And you store the return value in a pointer. Along with realloc and malloc, I'm going to check whether or not the returned pointer is null. If it's null, we're going to free the old string, and then we're going to exit, indicating that something bad happened. Then we're going to print out the characters in the string. So we should get sysc twice in this case. So let's run this and see what we get. And we do get sysc twice. Okay, so remember my original string, or I had a pointer that pointed at my original string, that was str. When I reallocated that memory, I stored the pointer to the reallocated memory in temp, right? Normally, what you're going to do in these situations is you're going to assign your temporary variable back to your original variable in this case, right? So I'm going to assign temp back to str, right? And so this makes it look like that str really has been reallocated to a new chunk of memory. I'm going to use str again to, I'm going to use the extra memory that I just reallocated. So now I'm going to concatenate 220 onto my string, and then print the string, and you get sys 220 in this case. And so there's an example of how that's basically the standard way that you would use realloc. Right, so pointer to existing memory, existing dynamically allocated memory, right? Reallocate. Check if you want to, right? Remember the discussion from the end of the last class where you don't necessarily have to check the return value from these memory allocation functions, and then reassign the new pointer back to the old one. Yeah, question. Yep. Call it as a parameter when you define as a temp. Why do you not down here? A little bit higher. When you make the character pointer temp. Here. Yeah. Why do you not put the? Oh, why don't you put asterisk in front of the str? Okay, so realloc is expecting a pointer to some allocated memory, right? So expecting a pointer, it's not expecting a string array. It's expecting a pointer, right? So there's my pointer, right? Str is a pointer, right? So here I can pass it str, right? You don't want to pass it the address of str. That would be the wrong thing to do, right? Similarly, you don't want to dereference str. If you dereference str, that gives you the first character of str, right? You want to give it a pointer to the memory that was allocated. Okay, so we're going to use realloc quite a bit later in this lecture. Okay, so once you've got a chunk of memory, either using malloc, calloc, or realloc, you're going to use the memory for whatever purposes, and then eventually you're no longer going to need that memory anymore, right? So your program might be done with the chunk of memory that you've allocated. It's at this point where you should, the responsible programmer should return the memory back to the operating system. And the way you do that is with free. So free, you give it a pointer, where PTR is a pointer to a block of memory that was dynamically allocated, right? So in other words, it's a pointer to memory that was returned by malloc, calloc, or realloc. It's supposed to be still a valid pointer when you pass it to free. Free will then release whatever memory is being pointed at back to the operating system. What you're not supposed to do is you should not call free twice with the same pointer. So you shouldn't free a pointer and then free it again immediately, right? So in other words, you only free a pointer as long as it's valid. As soon as you free the pointer, it's no longer valid. So a common piece of suggestion is to do the following. So here I'm going to allocate some memory using malloc, right? Then there's some chunk of code that uses p, right? Does whatever it needs to do. Eventually, we're done with p. You then free the memory that was allocated before, right? And then you immediately assign the value null to p. Right? What this lets you do is that as soon as you reassign a value back to p, you can pass null to free, and everything is fine. So free just ignores the null pointer. Right? It will also, if you accidentally use p for something else, so for example, suppose you accidentally dereference p, you'll know pretty quickly that you've done something wrong. Right? And so this is a common piece of advice that's given. As soon as you free a pointer, also set the pointer to null. That will hopefully prevent any other errors by passing p to free again, or by attempting to use p to do something because it's no longer valid as soon as you call free. Right, and that's it. So for dynamic memory allocation, that using dynamic memory allocation, that allows the programmer to control the lifetime of some chunk of memory. Right? Typically, the programmer puts an object or objects into that chunk of memory. Right? Often you'll put an array in, you might put a structure object in, you might even put an int in or something like that. Once you've allocated the block of memory, you're free. The programmer can use that block of memory for whatever they want. Right? So as long as the object, as long as the program needs that object to exist, you just keep on using that chunk of memory. Right? When you no longer need that object anymore, it's up to the programmer to release that chunk of memory by calling free. Right? Okay. And so that's the end of the dynamic memory allocation notebook. We're now actually going to use dynamic memory allocation to implement a proper string in C. Okay, so this is the QString notebook, or a simple string type. And so what I'm going to do here is I'm going to make our own string type. So something that sort of resembles a Java or a Python style string, not exactly, but resembles one, right? So we know that from our string discussion in C, C style strings are a little awkward to use. There's a lot of things that you have to pay attention to use them safely, right? They have to be null terminated. You have to allocate memory for them yourself. You have to deallocate memory for them when you're done, so on and so on and so forth. Right? One of the big problems with the C-style strings, right, is that if you need to write a function that does something with the string and you need the length of the string, finding the length of the string is in complexity big O of n, because C-style strings are just plain old arrays, and C doesn't know how big an array is. Languages like Python, C++, Java, they have dedicated string types, right? So in those languages, they have pretty rich string libraries. So their libraries can do lots and lots of things with strings. Finding the length of a string in those languages is in O1, because all of those languages record the length of the actual string. In Python and Java, your strings are immutable, right? So if you write a function that appears to modify a string, it's not actually modifying the string. It's doing something, computing a new string and returning a new string. If you compare that to C++, the C++ strings are immutable. So you have a string and you can change the characters of the string, you can change its length, and so on and so on and so forth. So this is the type of string that we want to implement today. Right? We want a mutable style string. So you want something where we can change its length, you can concatenate to it, you can, what else do we do with it? You can assign a string to a string, and so on and so on and so forth. So the approach we're going to use here is I think it's the simplest approach that new C programmers will be able to understand. If you look online, you'll find all sorts of third-party string libraries that play all sorts of cute tricks to extract the most performance that they can out of the string class, out of their string type. Our string type's not going to be, it's going to be easy to understand. Well, easy to understand, but it will be not as high performing as some of the other string types you can find on the internet. Okay, so to create our type, anytime you want to create your own type in C, you're essentially creating your own structure. Right? That's the C way of creating a new data type. So I want a structure called QString. Right? So Queen's string or something like that. Right? So we're going to start by declaring a structure that has nothing in it. So if you're doing this on your own, right, the way you would do this is you'd pop open your editor, right, you'd make a new file, right, and you'd start to type in your header file. Right? So we're going to place the structure itself in a header file. We're going to declare the functions that we want to be, the functions that operate on our structure in the header file. And then we're going to put the implementation somewhere else, right? So we're going to make a source code file and put all of the actual source code in that file. So whenever you make a header file, you always start out with an include yard, right? So if def, I'm going to call it my string now because I don't want to, because I have QString over here already. Right, so I'm just doing this for illustration purposes. right? And here we're going to do struct. So I'm just going to call this my string here, like that, right? And of course, I'm just going to jump over to QString now, right? And so notice that over here, right, I've got the exact same thing. I've got my header guard. I've got an include. So inside your own header files, it's very common to include the standard library header files here. I need standard def because I'm using size t here. And then I'm going to put my structure definition here. Right. So what's inside of our string? So let's go back to the notebook, talk about it here. Right. So inside of our string structure, I need a few things. At the very minimum, I need the array or a pointer to an array, well, a pointer to a chunk of memory where I can store the characters of the string. Right. So that's the minimum that I need, and that would be basically a C-style string. It would be convenient if we knew the length of the string. Right. So I'm going to put in a member called length. Right. Its type will be size t, so it's unsigned int of some kind. Right. So that holds the length of the string. I'm going to use an array of char to hold the characters of the string. Now, I don't know how big a string that the user is going to want to create, so I can't actually make an array here. So instead, what I'm going to do is I'm going to have a pointer. This pointer is going to point to some dynamically allocated memory that we will allocate when we know how big a string to actually create. And then finally, if we have a pointer to a chunk of memory, it's going to be useful to know how big a chunk of memory we actually have. Right? And so the length of the string, that's going to be the number of characters in the string. Right? This member capacity is how much space is available in the chunk of memory pointed at by data. Right? Our strings will also be null terminated so that if we want to, we can pass that pointer to a function that takes in a C-style string, and that function will still work correctly. Right. So for example, we would be able to pass data to string length, and that would actually be able to determine the length of the string. So we're still going to null terminate our strings. That's so that it's compatible with C-style strings. So our capacity is always greater than or equal to the length plus 1, right? Because we need to store the null terminator. Okay, so what we have here is just a structure. That's all that we have right now. Right? Surprisingly, you could actually use this thing the way it's defined. Right? So just like you can, if you make a class in Java and all you do is throw in some fields, you can immediately use that class. Right? Now the problem here is that when you actually go to when someone goes to use this structure, they have to do everything manually themselves. Right? So when they make a new string, they have to set the length themselves, they have to set the capacity themselves, they have to allocate the memory for data themselves, and so on and so on and so forth. So it's worth doing this once to see what our functions will actually end up doing for our users. So there's our structure. Here's a little main function. I'm going to make a pointer to a structure, right? And I'm going to allocate some memory to hold one of those one structure object. Right? So I'm going to use malloc and pass in the size of struct QString. That will let me make one structure object. Right? Inside that structure object, there's a length, there's a capacity, and there's a pointer to some data. Right? Now remember, when you use malloc, the memory that's allocated is completely random. You have no idea what's going to be there. So before you actually use S, we had better go in and set the members of S. This is what a constructor would do in Java, right? It would initialize the fields of your class. Here, we're going to initialize the members of our structure. Right? So I'm going to arbitrarily set the capacity of my string to 8. So we can hold the string length 7 in this thing. I'm going to malloc enough memory for that capacity. Right? And I'm going to store that pointer back in data. Right? So we now have a string, a QString object that has an array of length 8 inside of it. And now we can do something with that array. Right? We still don't know the length of the string yet. We know that we can hold up to 8 characters. we don't have a string yet, or we don't have data for the string. But I can use sprintf, or I guess str copy, to copy the string sys220 into our array. Whoops, sorry, into our array here, like that. Right. So here I'm using sprintf, right? Print that string into that buffer, right? Into that array. And now I know that I have a string of length 7. So away you go, right? And so these steps here, right there, right? Those are the steps that you would need to take if you wanted to allocate a new QString object and set the contents of that QString to sys220, right? So you can imagine there's going to be a function somewhere that takes in a C-style string, right, and returns a new QString object that holds the characters belonging to that C-style string. What's it going to do? Well, it's going to do exactly those steps there. All right, so I've got my string. What can I do with it? Well, I'm just going to print the contents of the string, right? Now I can't print the string itself, right, using printf or puts, right? I have to pass the array containing the characters to those functions. So that's what I'm going to do, right? I'm now done with my string object. So what do I have to do? I have to free whatever memory was allocated by my string object. Right now, the important thing to pay attention to here is that we actually called malloc twice. Right? We allocated array memory for our array, which we have a pointer to in data, but we also dynamically allocated the QString object itself. So I have to deallocate those things in reverse order. Right? I have to do it in reverse order because the array lives inside of the structure. So I have to deallocate the thing inside the structure first, and then deallocate the structure itself. So we free whatever memory is associated with the array belonging to our object S, and then finally we can free S itself. All right, so that's, if you look at that, that's worse than using a C-style string, right? That's really awkward. So we don't want to just give somebody the structure and say, here, go nuts, this is a string. We actually want to provide a bunch of functions that takes care of all of this stuff for them. Okay, so here we go. So what is our, oh, there's another example here. What are we doing here? Oh, I guess, okay. Back here. So back here, we allocated memory for that, for our array dynamically. Right. In this little example, you could get away with not allocating that memory dynamically. Right? So in this particular example, right, you could do something silly like this. Well, you could do something like this, which would work for this particular example. So I'm going to call it buffer 8. Right. So I'm going to make a little local array inside my main function. Right. And now instead of dynamically allocating memory and assigning that back to data, I'm just going to do this. Oops, sorry. Right. So I'm going to say our pointer now points at the first character of buff. Right. And now I'm going to run the rest of the code. If you actually run this, this works. Oh, sorry, it doesn't work. I can't do that. There we go. That works. Right. Notice that I can't free s.data because I didn't dynamically allocate it in this example. Sorry, when I changed it, I didn't dynamically allocate it. So you can't actually free it. Right. By passing in s.data to free, it's trying to free a locally allocated array, and it barfs. Right, but this does work. Right, you don't want to do it this way. Right, this works because we're only doing this in a little main function here. Right, the string object doesn't have to persist across multiple function calls. Right, so that's a bad idea. Right, and here's exactly what happens if you actually try to do something like this. Right, so there's our string again. Here I've got a function called bad string. Right, so this is the function that's going to do what I just did. Right, it's going to allocate memory for a structure. Right, we're going to make a little local array. Now remember, this array is local for this function, right? As soon as this function finishes, this array goes away, right? So when I do something like this, right? In other words, when I assign data, when I assign the local array to our pointer in our structure, right? When I return S down here, whoever ends up getting back the returned object doesn't have a valid data buffer anymore, right? That thing there, after the function returns, is no longer pointing at any valid memory because this thing here goes away as soon as the function returns. Sorry, this thing here goes away as soon as the function returns, right? So now, when you actually try to run this example here, oops, sorry, come on. Right, again, you get that double free or corruption error again, right? So when you attempt to deallocate that memory there, right, it barfs, right? Why does it barf? Because the array that was quote unquote allocated for it wasn't really allocated for it, right? It's a little local array that no longer exists, right? You might be surprised that it actually does print out 6220. So you call the function, right? It copies the characters into our local array, right? And then it prints out the local array, right? Notice that that actually did work. It's not guaranteed to work, right? Strictly speaking, this thing that data that str data is pointing at doesn't exist anymore, right? In this little toy program, it happens to still exist, right? So in other words, that memory hasn't actually disappeared or gone away or been used for something else. So it does in fact print out the correct string. But in a larger program, or if this object was passed around to a few other functions, and eventually you would end up with some sort of error, right? Basically, the error would be related to the fact that data is not pointing at a valid chunk of memory. Right, here we find out there's a problem when we try to free it. Okay, so remember, never return a pointer to a local array in C, right? It never works the way you want it to. So what functions should we provide for our string object or for our string type? So you can imagine hundreds, literally hundreds of functions that you might want to provide. Right? We don't have time to implement hundreds of functions, so we're going to implement a few of them. So we're going to do a function called new, right? So new is going to return a newly allocated and empty QString structure for the user to use. So this would be like calling the no argument constructor in Java, right? Or using the empty string in Java. From C string is the function that takes an existing C string, copies the characters from that string into a newly allocated QString object and returns the QString object. So that would be like calling a copy constructor in Java. Sorry, that'd be like calling a constructor in Java, where you copy another string. That's like a copy constructor in Java. So this one's going to copy another QString object, right? So it's going to copy another new string object, returning a new QString. Clear simply sets the length of the string to 0. Right? Get returns a character from a string. Set sets a character in the string. Assign lets you assign one string to another string. Right. So here you can assign the contents of right-hand side to the object left-hand side. Concat lets you do string concatenation. Remove range, rem range lets you remove a substring from a string. And then finally, destroy deallocates all of the memory that's associated with one of your string structures. Now, notice a few things that are going on here. I'm going to jump over back to code, right? So there's a few funny things that are happening here. Number one, all of our functions have a funny name, right? They're all QString underscore something, right? And the reason that we're doing this here is because remember in C, any function that appears at, well, sorry, all functions appear at global scope, right? Or have static storage duration, right? That's technically not the right term. Anyway, in a C program, all of your functions have to have unique names, right? So if I just called this new, right? And if I just called this, well, that's not a great example. Or if I just called this copy, right? Or if I just called this clear, right? There's a pretty good chance that in a large enough C program, that name is going to be used by something else, right? It's going to be used by another function. It's going to be used by another variable. And you won't be able to create a full, you won't be able to use our QString library in that program. And so what's very common to see in these types of libraries is that you append the name of the type in front of the name of all your functions, right? That's why they're all QString underscore something. That minimizes the possibility that somebody else has a library somewhere also called QString. And so that minimizes the chances of any of these name collisions. The other thing that's funny is all of our functions are returning pointers to QString structures. They're not returning plain old QString structures. Right. And so there's a couple of reasons why we're returning pointers instead of returning structures. So reason number one is that we're going to return null from our functions to indicate that something, to indicate that an error has occurred. Right. Remember, C doesn't have exceptions. They don't even, it doesn't really have any standard error handling techniques. So we're going to use one of the conventions for indicating an error. We're going to return null from these functions if something, if an error has occurred of some kind. There's a second reason, which is arguably more important. By returning a pointer, this lets us provide what's called an opaque type. And so we're going to talk about opaque types towards the end of the notebook, right? But if we want to provide an opaque type, we have to return pointers to objects instead of the structures themselves. Okay, so there's the header file, which I just showed you. Just skip through all of that. So let's actually look at the implementation of some of these functions. Right, and so new, from C string, and copy, these are all initialization functions. Right, they make a new QString object, right, and they initialize the structure members using information provided by the caller. Right, and so these all have this. These are all going to have the same pattern when you implement them. So let's look at our source code, right? So here's our header file, right? We've got our structured definition here, right? We have only the function declarations here. There's no implementation. So over in QString.c, this is where our implementation exists, right? Notice that in QString.c, we include our own header file, right? And so this is to make sure that, this is to make sure that when we define our functions here, we're actually defining everything that's in the header file. Okay, so our first function is new. Where to go? All right, so our first function is new, right? This is the function that allocates a new QString object. What is it? I forget exactly what it does. Pointer newly allocated QString. I guess it's supposed to be the empty string. So it's going to return a string of length 0. The array data will actually have a length equal to, it looks like 8. Right. So our QString default capacity, that's the size of a newly allocated empty string. Okay, so new, from C string, and copy, they all need to do something similar. Right, they all need to allocate a chunk of memory for our QString object. So they call a function called QString alloc that allocates specified chunk of memory, right, and returns a pointer to the newly allocated object. Right, so there's the call in new, right, there's the call in from C string, right, and there's the call in copy. Right. So up here, what does alloc do? All right, so alloc basically does everything that was on everything that was in the notebook, right? Step one, right? It allocates enough memory for the structure itself. Right? Step two, it allocates memory for the data array. Right? Step three, it sets the values of the members of the structure. So it sets the length to 0. It sets the capacity to whatever was passed to the argument that was passed into the function, right? And it sets the data pointer so that it points at the newly allocated buffer of characters, right? And it does a bunch of it does a bunch of error handling as well, right? So it actually does test if the returned pointer here is null, right? So if malloc fails, our function returns null, right? If calloc fails, our function returns null, right? But otherwise, it does everything that was in the notebook. So once you've got your allocated object, right, new can simply return the allocated object, right? So alloc makes a new empty C string, a new empty Q string. We can just return that object. From C string does the same thing as new, except it copies the contents of S into our allocated object. Right. So here, someone's going to pass in a standard C-style string. It has to be a null terminated string, so that's what we're assuming here, right? So for us to call alloc, we need to know how long is the string that we're copying. So we use string length to get the length of the string, right? When we call alloc, we pass in the length of the string plus 1 because we need to make sure the null terminator is stuck onto the end of the string. Assuming that alloc actually returns, does not return null, right? We can now set the length of our Q string, right? And we can copy the contents of S into our Q string object. So here I'm just going to use string copy. Again, you could use sprintf if you wanted to as well. So that copies the contents of S into our data buffer, right? And then we can return our newly allocated object, right? If that fails, Q is null. So we also end up returning null from here as well, which is what we want to happen. Copy is going to copy a new Q string object, right? So here we call alloc, right? Now, unlike in the previous example, we don't have to call the function to get the length of the string that we're copying, right? We can just copy the other array directly from our other Q string object, right? So in other words, we can we can set the capacity of our new Q string to be equal to the capacity of the one that we're copying, right? If this succeeds, we have a new Q string object. We can just copy the contents of the S into our new Q string, right? There's another function that will do that for us. It's called assign. So we're just going to call assign to actually copy the contents of S into our newly allocated object, right? And then we can return Q here as well, right? And so copy from C string and new, right? These all resemble a Java style constructor, right? They all make a new object, right? They all initialize the object, and then they return a pointer to the newly allocated object. Any questions about what's going on there? All right. If you're reading the notebook, you probably should read the notebook. There are some notes here, right? So there will be comments up here, right? And there are notes there are little numbered notes inside the notebook to explain what's going on in each one of those steps. Right. Similarly here. Right. Okay, we've now got a bunch of functions that don't change the capacity of the string. Right. So in other words, they don't have to manage any of the memory. So they don't have to reallocate the array, is essentially what I'm trying to say. So these are clear. Get gets a character. set sets a character of our string, and remove range removes a substring from inside of our string. Right. There's nothing particularly interesting here, but let's look at the functions anyway. Okay, so here's clear. Right, so what does clear do? Clear needs to basically set the size of the length of the string to 0. Right, so it wants to clear the characters from a string. Right, now you don't actually have to clear the characters in the string. Right, you don't. So in other words, you don't have to go into the array and 0 all the values. Right, all you have to do is set the length of the string to 0. Right, and you have to remember that our internally our array should look like a C-style string, right? So if you've got a C-style string whose length is 0, that means the first character of your string is just the null terminator. So we should do that, right? The rest of the characters, we don't care about them, right? So we don't have to overwrite them, right? And then we can return S, right? So clear is pretty straightforward. Get resembles car at in Java, right? So it gets a character from the string at a specified index. It indicates an error if you try to use an invalid index. Right. So our index type is unsigned int of some kind, right? Size t, so it's sometimes unsigned int. So I don't have to check if the index is less than 0. Right. But I do need to check if the index is greater than or equal to the length of the string. Right. If it is, that's not a valid index for our string. Right. Furthermore, I have to make sure that S is not null. Right. So if S is not null, if S is null, I'm also going to return null. Right. That's why I'm returning a pointer to a character. Right. I'm not returning the character itself. Right. If this function was to return the character itself, you run into a problem when you go to indicate an error. Right. What value do you return if there's some sort of error condition? Right. Who knows? Right. If you're returning a pointer, though, you can simply return null in this case. Okay, so I need a pointer to the character at that index. Right. Using pointer addition, this is dead easy. Right. It's just the start of the array plus the index. Right, and that gives you a pointer to the character at the given index. Set is going to be exactly the same thing, except we're going to change the character at that index. Right, so we're going to change the character of that index to C. I think this returns the old. It does. It returns the old character. Sorry, return res. Let me take a look at what this actually does. Set says returns pointer. Oh, returns a pointer to the character at the specified index. Okay. Okay, so we're going to use get to get the character at the index where we want to make the change. Right. We're going to go ahead and make the change to our character at that index. Right, so you just go into the array. Right, here I'm just going to use square bracket notation because it's easier than doing the dereference. Right. Go into the element at that index, set it to C, right, and return the pointer to the character that was changed. And so there's get, set, and clear. The last one here is remove range. That's all the way at the bottom of the source code file. So remove range removes a substring from our string. So you pass in the starting index of the substring that you want to remove, and you pass in one past the last character that you want to remove. So stop is one past the last character. So if you define stop as being one past the last character to remove, then the number of characters to remove is just stop minus start. Right. Right. So we need to remove, we want to remove that many characters from the string. Right. Now, what we're going to do here is we're going to use mem_move to shift everything past the end of the substring that we're moving forward into the string. Okay. I guess I should draw a picture for you. Okay, so imagine you have an array that represents a string. Okay. I would like to remove, so I'm just going to fill this up with some letters. Right, \0, so there's our null terminator. I'd like to remove the D, the E, and the F. Right, so that's 1, 2, 3, whoops, sorry, 3, 4, 5, and 6. Right. So I want to remove that. So start is going to be the 3. Stop is going to be the 6. Right. The number of characters that you're going to remove is 6 minus 3. 3, right? 1, 2, 3. Now, what I need to do is, if I'm going to remove the D, the E, the F, I have to take that G and shift it over to where the D is. And then I have to take the null terminator and stick it where the E is. Right? So the number of characters to move is the length of the string minus stop plus 1. Right? So I'll leave you to puzzle out whether or not that's correct. It is, it turns out. Right? And now I'm going to use mem move. Right? So I'm going to move that chunk of memory onto here. Right? So remember how mem move works. Right? That's the destination. Right? So that's where I want to move the memory to. So I want to move the memory to the D, right? Which is the start plus the index. Right? So start of the array plus the index gives me the address of where to move the memory to. Okay. Where do I want to move the memory from? I want to move the memory starting at the G. So that's the start of the array plus stop. Okay. How much memory do I need to move? I need to move that many characters. Right? Why am I using mem move instead of mem copy? Because the memory overlaps. Right? The memory that I'm copying overlaps with the memory that I'm copying into. Right? Or may overlap the memory that I'm copying into. Here it doesn't overlap, but it might. Right? So I have to use mem move. I can't use mem copy. How many characters have I removed? I've removed characters. I'm keeping track of the length of the string, so I have to subtract that from the length of the string. The capacity hasn't changed, right? My array hasn't changed at all, so I don't want to adjust the capacity of the array. Right? Finally, I can return a pointer to the original string because that's what this thing says it returns. All right, I guess I should stop there because we're just about out of time. The remaining functions in this structure, in our implementation, they all end up having to resize the array, right? And so there we're going to see how we're going to use realloc to actually reallocate the underlying array.